I'm going to talk about deep neural network models for nowcasting using satellite data. And let me start by saying that our satellite approaches are still in an early stage. They are not as well fleshed out as what you've seen for the radar data, but we still managed to obtain some good results. And I'm going to talk a bit about the approaches we've used for that, the kind of data we've worked with, and the results we have so far, and also what we plan to do for the future. Okay, so our research objectives here are to automate the process of nowcasting using machine learning in general and deep learning in particular. So as you might know from the previous presentations, nowcasting simply means to the ability to predict the weather for a short window into the future. So for example, we should be able to say if there's going to be some extreme events in the next 5 or 10 or 15 or so minutes. That helps people to take the necessary precautions to prepare, and it's a very active field of study, and it's of interest for meteorologists, and lately in the last few years also for machine learning researchers, because it's a field that's very approachable by machine learning algorithms due to its nature, which should become more obvious when I get into the data. So we want to obtain good performance in this regards. We'll also discuss the performance metrics that we've used and how we judge what a good algorithm for nowcasting prediction implies. And we want to develop robust models, which means that they should be usable for different types of radar data, for different regions of the world, and so on. So they shouldn't be limited to a particular satellite or the data given to us by a particular satellite, or they shouldn't be limited to a particular geographical region. We should have some architecture, some model architecture that ideally works in every or as many scenarios as possible. So let's talk about the existing approaches for this problem. As far as we were able to find in the literature, most of these are RNN based. And RNN stands for recurrent neural network. The most common types of recurrent neural networks are the LSTM-based networks and the GRU, gated recurrent unit networks. These usually obtain the best results in various similar problems. And the way they work is that unlike classical algorithms, they deal with time series data. So we can imagine the satellite data as being a time series, right? So if the satellite feeds us images every, let's say, 5 minutes, then the data for an hour can represent a time series. And recurrent neural networks work best with these types of time series, but they are cumbersome in many ways. For example, they take a lot of resources to train and a lot of time. Building these time series requires a lot of data, hundreds of thousands of images for these RNN-based models to learn properly and to be able to produce decent results. So they can be quite untractable in practice. You would need to train them for a long time. You would need to spend a lot of time making sure that they deliver the correct predictions. And you would also need powerful machines to deliver the predictions themselves. So right now we haven't gone down this beaten path of using RNN-based models. And we took a slightly more conservative approach. And I'll get into that in a minute. But first, let me say that our experiments are conducted on 10 days of data, 5 from 2018 and 5 from 2020. And they were published in an article in CAS, which was recently accepted. And our approach, getting back to the model part, is an exception style deep convolutional neural network with T and T plus 1 pairs, where the difference between T and T plus 1 is 15 minutes. And let me elaborate on that a bit. So recall that I said that for recurrent networks, you need that time series data, which usually involves something like an image taken an hour ago, an image taken an hour minus 5 minutes ago, and so on. So a series of images. Well, with our deep convolutional neural network, we basically reduce that series to two images. So we have an image at timestamp t and an image at timestamp t plus 1. And we want to train our deep CNN to output the image at t plus 1 given the image at time step t. So we want it to predict one time step into the future. And by one time step, for our data at least, we mean a 15-minute window. Okay, so that's what I mean with this notation. T plus 1 is actually T plus 15 minutes. So one time window or time step in our case is 15 minutes at least for this satellite and this data. All right, and this is a flat model. We will see what I mean by that. I will also present the model architecture in detail. It basically means that there aren't many branches in it, and it makes as much use as possible of classical convolutions without any other complications and complexities. Okay, and we obtained decent results for this type of model. We're going to take a look at them. Again, this is, I want to emphasize that this is a conservative model, so it's much faster to train than a recurrent model. It requires much less data to give decent results. And it's generally much faster to work with, to develop, to make adjustments to, and so on. Okay, so this is an example of how, first of all, how our satellite data looks like for one of the products. We've used 5 products in this experiment. So we have used a window across with Romania in the center and some of its neighbors or parts of its neighbors. They look just like any RGB image. They actually are were given to us as color PNG images. So this is how they look like. Different products can have slightly different color palettes. This is mostly blue and red. There are others that have slightly different color schemes, but the same core structure really. So what we can see here is an example of one of those T and T plus 1 pairs I was telling you about. More specifically, they are the T plus 1 pair, the T plus 1 component. The one on the left is the real one, and the one on the right is the predicted one. So looking at these two from afar, they look quite good. So the prediction is very close to the ground truth, which is very good for us. Looking at them in a bit more detail, we will be able to tell what shortcomings the algorithm has and where we need to do more work. And let me tell you what I mean by that. For example, if you look around here at the border with Moldova and Ukraine, in the predicted image, you will see some artifacts. They are green and reddish, and they show up in different locations across the border, so across this white line, these white lines. Those artifacts aren't that important in my opinion because they can just be ignored. But what's a bit more important, I think, is that the prediction is a bit shifted. So that's harder to see, but if we look here across the border with Hungary, for example, here, right, you can see that this red blob here in the ground truth image is closer to the border than it is in the predicted image. And it's the same here with this blob here towards the south of Hungary. It's more towards the south here in the ground truth, and more towards the north here, or less towards the south in the predicted image, which means that our model doesn't do as great of a job as we would like it to do in learning the movements of these weather patterns. So that's definitely a shortcoming, but it still manages to learn these movements a bit, enough to outperform similar non-recurrent approaches and a baseline approach of our own. So here we have some actual numbers. So the products, the products I was telling you about, the 5 products. We've used for the evaluation measure the mean absolute error and the normalized mean absolute error. And we've also introduced a baseline convolutional neural network model, which is something very naive, where we just apply a few convolutional layers. So there is nothing deep about it. We can see here that for most of the products, our DeePSat model, that is the deep model, performs better. In our article, we detail this and compare it with existing literature approaches as well. And for those that it doesn't do better than the baseline CNN, it still does very close, and the differences are definitely not human readable. So the outputs, if we would look at them like this side by side, we wouldn't really be able to tell a difference with our bare eyes. Okay, before I show you a few more examples, I want to tell you about our future plans. So for future work, we have to take into account that the RNN-based models do perform better in practice. And we would want a best of both worlds approach. So in the literature, the RNN-based models obtain mean absolute error values, some of them even below 1. So that's over 10 times better than our own. So that is definitely something we have to consider. So we would want a best of both worlds approach, in that we would like to be able to develop an RNN-based model that is a bit more lightweight, that doesn't require huge amounts of data and training time and computing resources. And that still significantly reduces our existing errors. That's our main goal. And let me show you a few other things I've prepared here. So I made this GIF, hopefully you can see it. This is with another product, and this is what our model predicts. And we'll just let it run for a few seconds so that you get an idea of what's going on. So you can see there are a few artifacts still, but it's very decent and usable, we think. And now I will show you the real pattern. So I believe they are very similar. And again, we might be able to identify small inaccuracies if we were to look at them side by side and carefully analyze each frame. But overall, I think it does a decent job considering the complexities of the problem. This is how the model looks like, the raw model. So I'm not even going to zoom in because I'm going to show you a compressed version of this. This is just to get an idea of how deep the model is. Each of these rectangles represents a component of the model, basically. So we have tens of these. And to show you the compressed version of that, it looks like this. This is a lot more readable, I think. So as you can see, it just uses basic convolutions grouped into blocks. Those blocks are repeated various times, a certain number of times. This block is repeated 3 times. This one is repeated 4 times. And we add various helper functions to the results of the convolutions, such as the rectified linear unit and batch normalization. So this is how the model looks. And also, if you look here, these numbers everywhere represents the number of filters in our convolutions. The lower the number of filters is, the faster the training time and the prediction time as well. So being able to achieve these accuracies with such a low number of filters is a very good thing. And it definitely gives us hope for what we want to do with RNN-based models. We do believe we will be able to come up with a lightweight model there as well. Yeah, so this is the one I was talking about with the repeated blocks here and the number of filters here. Okay, this is the same thing as what you saw when the screen froze, but it's compressed in a more human readable format. Okay, so that's all we have so far regarding the satellite data. If there are any questions, I will try to answer them.